Hello and welcome to yet another review session for your final exam in Calculus 3208. Still looking at applications of derivatives and specifically optimization, and even more specifically now we're going to look at some optimization problems that involve maximizing volume. All right, fun stuff. So let's get started. So not really any detail here. We're going to focus on solving problems to maximize volume. So let's get right down to business. So this first situation we have an open top box that's going to be created from a 20 centimeter by 40 centimeter sheet of cardboard. Okay, so we've got 20 centimeters on the shorter side, and we've got 40 on the longer side. And it says we're going to cut congruent squares from each corner and fold up the resulting flaps, and that's going to make us an open top box. So what is the maximum possible volume of such a box? Well, we think about the decision that has to be made here. It's basically how big should we cut those squares so that when we fold this thing up, we get the biggest box we can make. So what we're going to do is we're going to call the length of the squares on their edges to be x. So all the way around this box, I'm going to have these little x's. All these squares will have the same length. They'll all be x. Okay, so now we've got to figure out what this box is going to look like. So when I create this box, pardon my poor artistic ability here, I get this open top box that's going to look kind of like this. All right. So the height of the box will be the same as the length of the square when I fold it up, so that'll be x. And then sort of the length along the side of the box, if we just fold that up, is going to be, well, it was 20 centimeters, and now it's going to be 20 minus 2x. And then along the front of the box, it was 40, and so that'll be 40 minus 2x because we cut 2 x's out of that. So then our total volume equation here is going to be volume equals x by 20 minus 2x by 40 minus 2x. Okay, so we can expand that stuff and put it all together, and I think we get 4x cubed minus 120x squared, let me see, plus 800x. Okay, and if we want to put some restrictions on our variable for our domain here, pretty sure x would have to be bigger than 0 or we're not going to get any volume there. And if x is any bigger than half of that side, we're going to be in trouble because we don't have enough for that. So we'll say x has to be less than or equal to 10. But I think in both of those situations, if we hit the endpoint, we get 0 volume. So both of those are not going to count when we look for our maximum or our absolute max here. So let's go after a derivative now. So if we go after a derivative v prime, that's going to give us 12x squared minus 240x plus 800. And then we'll let that equal to 0 to look for our critical values here. And everything is divisible by 4, so I can reduce my equation a little bit here. So that's going to give us 3x squared minus 60x plus 200. And I don't think that's going to factor very nicely. So it looks like quadratic formula is going to have to come out of the archives here for a second. So x will be equal to negative b, so 60 plus or minus the square root of b squared. So 60 squared is 3600. And then we're going to subtract 4 times a, which is 3, times c, which is 200. And then all of that has to be divided by 2 times a, which is going to be 2 times 3, or 6. So a handy-dandy calculator is going to be necessary. And it turns out, let's see, we get roots here of 4.2 and 15.8. So one of these things is not like the others. 15.8 is no good to us because it's outside of our restricted domain. So it looks like x is going to have to be 4.2. Let's see what the actual volume would work out to be at that point. So the volume at that point, at 4.2, would work out to be 4.2 times 20 minus 2 times 4.2 times 40 minus 2 times 4.2. And if we crunch those numbers in a magic calculator, I'm getting somewhere in the vicinity of 1,540 cubic centimeters. So a nice big box that we got there to carry all of our calculators. Okay, so let's move on to the next question. Oh, this looks fun. Find the dimensions of the largest right circular cylinder that can be inscribed inside a sphere of radius 4 centimeters. All right, so I've got to find the dimensions of the largest cylinder that I can inscribe inside a sphere if its radius is 4 centimeters, and we can see on the diagram here, showing that the diameter all the way across is going to be 8. So let's start with a volume equation. So we're trying to find the volume of the cylinder here. So the volume of a cylinder is going to be pi r squared times its height. Okay. Now, we're going to need a secondary relationship for sure because I've got two variables, and hopefully something about the geometry here is going to help us out. All right, so let's draw on here. You think that we've got two different radii happening. We've got the radius of the cylinder right there, and then what I'm going to do is I'm going to draw a line from the center of the top of the cylinder to the center of the sphere, like this. And then I'm going to connect those up to make a right angle triangle. And you can see that the hypotenuse of my triangle is actually going from the center of the sphere to a point on its surface. So that's the radius of the sphere, which is 4 centimeters. And the two legs of my right triangle will be the height of the cylinder divided by 2, because it's halfway there, and the radius of the cylinder. So what that allows us to do is to get a secondary relationship using Pythagorean theorem. So we can see that r squared plus h divided by 2 squared is going to be equal to 4 squared. Whoops. 4 squared is 16. Let's just call it 16. All right. So then we're going to be able to replace one of our variables in our equation that we have. They're probably going to be easiest just to replace r squared, and then they don't have to square anything in the formula. So r squared will be 16, subtract h squared over 4. So we have the volume equals pi times 16 minus h squared on 4 by h. Okay, so then if I put all that together, simplifying my volume equation, I have 16 pi h minus, let's see, pi h cubed all over 4. All right, so now I have my volume equation, and I guess I'm going to look for some critical values here. I could put some restrictions on the value of my height. Certainly the height can't be any bigger than the radius, and it can't be any smaller than 0. So let's say that the height is going to have to be bigger than or equal to 0 or less than or equal to 4. So those are going to be restrictions. Of course, neither one of those endpoints will matter a whole lot for this problem because they both give us volumes of 0. But just so we know that we have some endpoints. And then we'll take our derivative. So v prime will be 16 pi minus 3 pi h squared all over 4. And so I let that equal to 0 to look for critical values. So 0 equals 16 pi minus 3 pi h squared over 4. And so I solve for h here. Let's subtract the 3 pi h squared over 4 onto the other side. And we can see that a quick division would get rid of the pi's. And so h squared then would be equal to 4 times 16, which is 64, over 3, and then square rooted to give us just a value for h. Okay, and I think my handy-dandy calculator tells me that that's about 4.6 centimeters. So I should make the height of my cylinder 4.6 centimeters. It did ask for the dimensions, so we should get the radius as well. So the radius, I'm just going to use this equation. It'll be the square root of 16 minus 4.6 squared over 4, and that turns out to be 3.3 centimeters. So those are going to be the dimensions of the biggest cylinder that we can inscribe inside that sphere. Good question. That's a fun one. All right, one more. Let's see. What are the dimensions of the largest cylinder, ooh, another one, that can be inscribed inside a right circular cone with height of 8 and base radius of 4? So again, we want to find the volume of a cylinder, which is pi r squared times h. And the tricky business with this, as always, is finding that secondary relationship. Okay. And so to find that secondary relationship here, we really have to think outside the box, or outside the cone, as it were. So what I've done is I've created a little graph over here on the right. And that graph is sort of, if I just sort of squashed that cone and flattened it out and just drew an outline of it on a two-dimensional graph, we could see that the height of the cone could be plotted here as 8, and the radius of the cone would actually be the length of this side right here if I just think of a distance on x to go from that point to that one. And so since we have that, we can get a relationship between the radius and the height of the cylinder, believe it or not, because at any point on the line that we see here on the right, that would be the radius of the cylinder from over here, and this one would be the height of the cylinder from over there, right there. And so that's like the x and y coordinates of any point on that line. So we just need the equation of the line, and that will give us a relationship between radius and height. And that's fairly simple to do because we have a y-intercept here at 8 and an x-intercept here at 4. So that's a linear equation with a slope of -2 and a y-intercept at 8. And that gives us our relationship between height and radius, like so. Alrighty, so over here then, I can make a substitution with my secondary relationship to replace the height variable this time and make it -2 times the radius plus 8. So my volume will be -2 pi r cubed, come on pi, -2 pi r cubed, and plus 8 pi r squared. Alright, so there's a good one. So what we have to do now is take the derivative of all of this mess so we can look for critical values. We should restrict this, by the way. The radius here is going to have to be greater than or equal to 0 and less than or equal to 4, so we can see that. Probably not going to be an issue because, again, those endpoints are not going to make any volume. So our derivative of the volume equation will be -6 pi r squared plus 16 pi r. So solving that, we're going to have 6 pi r squared equals, oh sorry, I've got to factor that though. Excuse me. So 0 equals, let's factor out a common factor of, let's say, 2r. So if I make it equal to 0, take out a common factor of 2 pi r, we will even say. Then we've got left over here, we've got -3r plus 8 inside. And so this means that either r is equal to 0, which doesn't give us any volume at all, or r would be equal to 8 over 3, which I think is going to be our winning candidate, isn't it? So if r equals 8 over 3, then we've got to find our height. So the height at that same location is going to be -2 times 8/3 plus 8, which is 16 over, wow, look at that, it works out to be 8/3 as well. So we get the same height and radius. Both of them are going to be 8/3, and that would give us the biggest cylinder that we can sort of squeeze inside that cone. All right, lots of fun with that one. Here's the your turn question. So take a look through that. It's a tricky one, but you're all bright young folks. I'm sure you'll figure it out. And if not, the solution is posted for you here, and you can check your answers. And the summary of the key ideas here, it's all the same stuff we've been doing, but the real trick here is using those secondary relationships. They're very key to figuring out these max-min problems. So good luck with that. I hope your studying is going well, and if you have any questions, put them up on D2L. Thanks.